In this demonstration, you'll learn about setting up an overset meshing problem with dynamic or moving meshes. This video focuses on the problem of store separation, which, for this case, is a simplified rescue pod being dropped from a moving airplane. As the pod falls, it's subjected to pressure, viscous drag, and gravitational forces, which cause the pod to rotate about its center of gravity. Because this is a more involved overset meshing problem, I'm assuming that you have a working knowledge of overset meshing and its associated terminology. There's an introductory overset video that's linked in this video's description. I'll begin with just the background mesh loaded. This mesh has 3 different zones so that I can have a greater level of refinement where the pod will be falling and less refinement as we get further away. Dividing the background mesh into multiple zones allows for non-conformal interfaces between the other zones that won't be part of the overset interface, as background meshes can't have non-conformal interfaces between them if they're part of the same overset interface. I've already created the mesh interfaces between these zones, as you can see here in the tree. Now I'll append the component mesh, which contains the pod that will be dropping from the hold. Before you create an overset interface between the component and background, you want to ensure that any overset boundaries are specified. During mesh creation, I gave descriptive names to the boundaries like pressure inlet and overset boundary. Ansys meshing automatically assigned the correct boundary types based on these names, but not all meshers work this way, so it's important to verify that all of the boundaries are assigned as you expect. Had these boundaries not come in correctly, I can easily change their types using a right click. With the overset boundary appropriately specified, I can create the overset interface. After I give the interface a name, I can select the zones that are participating in the interface. In this case, I'm only selecting fluid background, as it's the only background zone that the moving component mesh will be passing through. As with any time you make changes to the mesh connectivity, it's good practice to perform a mesh check to confirm there aren't any pending errors. Next, I'll specify the boundary distance donor priority method. Because of the uniformity of the cell sizes between the component and the background, the boundary distance method will guide the interface to the middle, reducing cell overlap between the component and background. When creating your meshes, you'll want to ensure that you have at least 4 cells in the gap between the component and the background meshes coming from each wall. As you can see with these meshes, I have far more than the recommended minimum. Here is a coarser mesh for the same case that only has 2 cells between the wall of the pod and the vertical bay wall of the background, which I'll use to demonstrate why it's important to have more cells in the gap. During initialization, Fluent performs the hole cutting, which creates the overset intersection. But if you want to create the intersection before initializing, then you need to enable expert commands. The donor search can fail due to orphan cells, which are receptor cells that can't find a valid donor cell. The presence of orphan cells generally indicates that there is insufficient overlap between the meshes, or that the mesh resolutions don't match well. You can mark orphan cells, which will likely indicate where the mesh overlap needs to be increased. I'll mark my orphan cells by using the mark cells text command. It automatically creates a cell register with the orphans, which I can then display via the Manage Adaption Registers dialog box. This case has 1 orphan, which you can see is located in the gap where I didn't have at least the recommended 4 cells. Here we are back at the refined case, which doesn't have any orphans due to the finer resolution and increased number of cells in the gap. I'm skipping over the remainder of the case setup and boundary conditions specification, which included loading a UDF defining the mass of the pod and its ejection forces and moments. Note that before you begin solving your transient dynamic mesh case, you'll want to reach a converged steady-state solution. Here are the 2 dynamic mesh zones that I've created for this problem. One is for the component mesh surrounding the falling pod, and the other is for the pod itself. The component zone doesn't have any effect on the forces acting on the pod, so I've enabled passive. And here's the dynamic mesh zone for the pod, which has passive disabled, so that the forces are calculated on the walls of the pod as it falls. I'm increasing the overset verbosity for increased overset reporting in the console during the calculation run. In particular, I'm looking for Fluent to tell me how many cells have been directly converted from dead to solve. This is an issue as dead cells have no information, so they need to go from dead to receptor to solve. Otherwise, this can lead to solution inaccuracies. If, in your transcript review, you see more than a small number of cells going from dead to solve, then you need to decrease the time step size. Here is a velocity vectors animation I created from this simulation. And this is an animation of a more realistic store problem that has also been solved using Fluent. This is a model that's been used for validation, and the results match well with experimental data. This concludes this demonstration of overset meshing and dynamic meshes. Thanks for watching.